There is mathematical induction, a discussion agenda. First, we shall introduce the technique which is known as mathematical induction. Secondly, we shall prove some summation results with the help of mathematical induction technique. Some inequalities will also be derived. Further, some divisibility result will also be discussed. First, introduction to mathematical induction. Mathematical induction is basically a technique which is used for proving results, especially when we have to prove a proposition for all positive integer n. This technique consists of two steps. First step is known as base step, while the second step is known as inductive step. In the base step, we prove the given proposition for starting integer, and in the inductive step we first suppose that the given proposition is true for n is equal to k, and then on the basis of this assumption we show that the given proposition is true for n is equal to k plus 1. Properly we can define the principle of mathematical induction as base step. We verify in this step that the given proposition, if we denote the given proposition by p of 1 is true. Note that it is not necessary that in the base step we shall always take n is equal to 1. It's depend upon the given proposition. If the given proposition starts from n is equal to 3, then we should prove the given proposition in the base step for n is equal to 3. If the given proposition starts from n is equal to 5, then in that case we should take n is equal to 5 on the base step. If the given, we have to prove the given proposition for non-negative integers, then in that case we should take n is equal to 0. And in the inductive step, basically we have to show the conditional statement p of k implies p of k plus 1. That is, we have to assume that p of k is true, and then with the help of this p of k we shall show p of k plus 1. Proving summation result. The first result is show that 1 plus 3 plus 5 up to 2n minus 1 is equal to n square. That is, this result says that the sum of the first n odd integer is n square. We prove this proposition with the help of mathematical induction. So let's denote this given proposition by p of n, and here the given proposition is obviously true for n is equal to 1. If we take n is equal to 1, then 2 times 1 minus 1 is 1, and 1 square is 1. Right? So this means the base step is complete. Next we proceed to inductive step. In inductive step we suppose that the given proposition is true for n is equal to k, that is 1 plus 3 plus 5 up to 2k minus 1 is equal to k square, and we need to prove this for n is equal to k plus 1. For this 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1, as 1 plus 3 plus 5 up to 2k minus 1 by assumption is k square plus 2k plus 1. This is equal to k square and plus 2k plus 1. We can write from this k plus 1 whole square, and that was our goal. So this means by mathematical induction technique we have shown that the sum of the first n odd integer is n square. Question. Use mathematical induction to show that 1 plus 2 plus 2 square plus 2 raised to the power n is equal to 2 raised to the power n plus 1 minus 1 for all non-negative integers n. For all non-negative integers n. Here we have to prove this proposition for all non-negative integers n, therefore the starting integer will be here 0. So let us label this proposition by p of n. That is, p of n is here 1 plus 2 plus 2 square plus 2 raised to the power n is equal to 2 raised to the power n plus 1 minus 1. Now base step. By taking n is equal to 0, we get 2 raised to the power 0 is 1, 2 raised to the power 1 minus 1 is 1. This completes the basic step. Next, inductive step. And inductive step assume that the given proposition is true for any arbitrary integer k. That is 1 plus 2 plus 2 square plus 2 raised to the power k is equal to 2 raised to the power k plus 1 minus 1. We show that the given proposition is true for n is equal to k plus 1 on the basis of the assumption step. Since 1 plus 2 plus 2 square plus 2 raised to the power k plus 2 raised to the power k plus 1 is equal to 2 raised to the power k plus 1 plus 1 minus 1, as 1 plus 2 plus 2 square plus 2 raised to the power k by assumption is equal to 2 raised to the power k plus 1 minus 1, and plus 2 raised to the power k plus 1. If we combine 2 raised to the power k plus 1 plus 2 raised to the power k plus 1, then from 2 raised to the power k plus 1 plus 2 raised to the power k plus 1, we can write 2 times 2 raised to the power k plus 1. And from 2 times 2 raised to the power k plus 1, we can write 2 raised to the power k plus 1 plus 1 using indices rule, which is equal to 2 raised to the power k plus 2 minus 1. Under the assumption of p raised to the power of pk, we see that this 1 plus 2 plus 2 square plus 2 raised to the power k plus 2 raised to the power k plus 1 is 2 raised to the power k plus 2 minus 1, and this 2 raised to the power k plus 2 you can write as 2 raised to the power k plus 1 minus 1. And this is what we wish to prove. So according to mathematical induction, we can say that we have proved the given proposition. Next, we are going to prove some inequalities. The first inequality is show that n is less than 2 raised to the power n for all positive integer n. Here in the basic step, you should start from n is equal to 1. But this is not difficult to prove this inequality by using mathematical induction technique. Therefore, we skip here and it is left as a homework for the students. Next question is use mathematical induction to prove that 2 raised to the power n is less than n factorial for every integer n with n is greater than or equal to 4. Here the starting integer is 4. Note that this inequality does not hold if we take n is equal to 1, 2 or 3. Let us denote this proposition by p of n. Then in the basic step, if we take n is equal to 4, here the proposition start from n is equal to 4, that is the starting integer is 4. That's why I am taking n is equal to 4 in the basic step. And the basic step 2 raised to the power 4 is 16 and 4 factorial is 24, and we know 16 is less than 24, then this means we have shown that the given proposition p of n is true for n is equal to 4. Thus the basic step complete, and we proceed to inductive step. And inductive step, we have assumed that 2 raised to the power k is less than k factorial, and we are interested in the proof of the inequality 2 raised to the power k plus 1 less than k plus 1 factorial. Since 2 raised to the power k plus 1 can be written as 2.2 raised to the power k. Further, by assumption 2 raised to the power k is less than k factorial, therefore I can write from the above as 2.k factorial, and 2 is less than k plus 1, as the smallest possible value for k is 4 and 4 plus 1 is 5, and we know 2 is less than 5, therefore from the above inequality we can write k plus 1 into k factorial, which is k plus 1 factorial, which was our goal. Thus, by mathematical induction technique, we can say that we have proven the given proposition. Next, harmonic numbers. Before going to harmonic numbers, recall the definition of harmonic sequence. Harmonic sequences basically we generate from arithmetic sequence. If we take the reciprocal of the terms of arithmetic sequence or progression, because sequence is also known as progression, then we get a harmonic sequence. Assume that here we have commas instead of plus. Now if I take the reciprocal of these terms, then this will be 1, this will be 2, this will be 3, this will be j. Right? 2 minus 1 is 1, 3 minus 2 is 1, and 4 minus 3 is 1. J minus 1 is 1. This means that the gap between any two consecutive numbers is same. So if we take the reciprocal of the term, these terms, then we get arithmetic sequence. And then this means that this is a harmonic sequence. Here we are interested in harmonic numbers basically. What are harmonic numbers? Harmonic numbers are denoted by H subscript j. Harmonic numbers are basically the sum of first j numbers. If we say H subscript j means the sum of the first j terms of a harmonic sequence. H1 means 1, H2 means the sum of the first two terms of harmonic sequence, 1 plus 1 over 2, and the H3 means the sum of the first three terms of the harmonic sequence, 1 over 2, 1 over 3, 1 over j. H5 means the sum of the first 5 terms of the harmonic sequence, 1 over 2, 1 over 3, 1 over 4, 1 over 5. In general, H subscript G means the sum of the first j terms of the harmonic sequence, 1 over 2, 1 over 3, up to 1 over j. Here question is show that H subscript 2 raised to the power n is greater than or equal to 1 plus n by 2 whenever n is non-negative integer. H subscript 2 raised to the power n means the sum of the first 2 raised to the power n terms of the harmonic sequence, 1 over 2, 1 over 3, up to 1 over 2 raised to the power n. Here n is non-negative integer, and then this means we should take the starting integer n is equal to 0 in this case. Let us denote the given proposition by p of n. First, the basis step. By taking n is equal to 0, we get h2 raised to the power 0, which is h1, and h1 is 1, which is 1 plus 0 by 2. So, this means we have completed the basis step. Next, inductive step. In inductive step, we assume that the given proposition p of n is true for n is equal to k. That is, h raised to the power 2, h subscript 2 raised to the power k is greater or equal to 1 plus k by 2. K is any arbitrary integer. And our goal is to show that h subscript 2 raised to the power k plus 1 is greater or equal to 1 plus k plus 1 divided by 2. Here, h subscript 2 raised to the power k plus 1, according to definition of harmonic number, is equal to 1 plus 1 over 2 plus 1 over 3 plus 1 over 2 raised to the power k plus 1 over 2 raised to the power k plus 1 plus 1 over 2 raised to the power k plus 1. H subscript 2 raised to the power k plus 1 means the sum of the first 2 raised to the power k plus 1 terms of the harmonic sequence, 1 over 2, 1 over 3, up to 1 over 2 raised to the power k plus 1. Last term is 1 over 2 raised to the power k plus 1. But we know that 1 over 2 raised to the power k is included in this summation, as 1 is greater than 1 over 2, 1 over 3 is greater than 1 over 4. This is here 1 over 2 raised to the power k is also greater than 1 over 2 raised to the power k plus 1. Further, this sum that is 1 over 2, 1 over 3, 1 over 2k, again according to harmonic numbers, can be replaced by h subscript 2 raised to the power k. and plus 1 over 2 raised to the power k plus 1 plus 1 over 2 raised to the power whole k plus 1, which is greater or equal to 1 plus k by 2. Here we have used the assumption step. As according to assumption step, h subscript 2 raised to the power k is greater or equal to 1 plus k by 2. Therefore, we can replace this by 1 plus k by 2. We can replace h subscript 2 raised to the power k by 1 plus k by 2. But we should replace the equality also by inequality. And further, we can write from this as 1 plus k by 2 plus 2 raised to the power k divided by 1 over 2 raised to the power k plus 1. These are totally 2 raised to the power k terms. First term is 1 over 2 raised to the power k plus 1, plus the second term is 1 over 2 raised to the power k plus 2, third term is 1 over 2 raised to the power k plus 3. Continuing in this manner, we can write this last term as 1 over 2 raised to the power k dot 2. 1 over 2 raised to the power k dot 2. Now, this means 2 times 2 raised to the power k. 2 times 2 raised to the power k can be written as 2 raised to the power k plus 2 raised to the power k. So this means I can replace this 1 over 2 raised to the power k plus 1 by 1 over 2 raised to the power k plus 2 raised to the power k. From this we can say that there are totally 2 raised to the power k term, 1 plus 2 plus 3 plus up to 2 raised to the power k plus 2 raised to the power k. Then from this we can say that there are totally 2 raised to the power k terms. 2 raised to the power k times 1 over 2 raised to the power k plus 1. If we replace and this sum each term by 1 over 2 raised to the power k plus 1, as 1 over 2 raised to the power k plus 1 is greater than 1 over 2 raised to the power k plus 1. If we replace the first term by 1 over 2 raised to the power k plus 1, second term also by 1 over 2 raised to the power k plus 1, third term also by 1 over 2 raised to the power k plus 1, then the above summation must also be less than 2 raised to the power k times 1 over 2 raised to the power k plus 1. Now one can cancel out 2 raised to the power k, 2 raised to the power k, and we will be left 1 over 2. 1 plus k by 2 plus 1 over 2. This is greater or equal to 1 plus k plus 1 divided by 2. But we should take this here equality rather than inequality. This establishes the inductive step of the proof, and thus according to mathematical induction we complete the proof of the given proposition. And now we discuss some divisibility results. First result is prove that nq minus n is divisible by 3 whenever n is positive integer. We prove this by technique mathematical induction. Let the given proposition p of n. Then taking n is equal to 1, we get 1q minus 1 is 0 and 0 is divisible by 3. This completes the basic step. We proceed to inductive step, and this inductive step we assume that the given proposition p of n is true for n is equal to k, that is q minus k is divisible by 3. On the basis of this assumption step, we show that k plus 1 cube minus k plus 1 is divisible by 3. Since k plus 1 cube minus k plus 1 is equal to this, as a plus b whole cube is equal to a cube plus b cube plus 3a square b plus 3ab square. According to this formula, we can write this as minus k plus 1, which is k cube minus k plus 3 times k square plus k. As according to assumption, k cube minus k is divisible by 3, and this term is also divisible by 3, being a multiple of 3. So the sum of two numbers such that each of them is divisible by 3 is also divisible by 3. Thus we complete the proof of the given proposition. Next result says that prove that 7 raised to the power n plus 2 plus 8 raised to the power 2n plus 1 is divisible by 57 for every non-negative integer, and here we should start from n is equal to 0. Let the given proposition as p of n, then we prove this proposition p of n by using the technique of mathematical induction. So according to mathematical induction technique, first we complete the basis step. By taking n is equal to 0, we get 7 raised to the power 2 plus 8. And 7 raised to the power 2 plus 8 is 57, and obviously 57 is divisible by 57. This completes the basis step. Now inductive step. In inductive step, we assume that the given proposition is true for n is equal to k, that is 7 raised to the power k plus 2 plus 8 raised to the power k plus 1 is divisible by 57. And our goal is to show that 7 raised to the power k plus 1 plus 2 plus 8 raised to the power 2 into k plus 1 is divisible by 57. We start from 7 raised to the power k plus 1 plus 2 plus 8 raised to the power 2 k plus 1 plus 1. And this is equal to 7 raised to the power k plus 3. This is equal to 8 raised to the power 2k plus 3. And next step, we can break this 7 raised to the power k plus 3 as, and 8 raised to the power 2k plus 3 as we shall use here the assumption step, that is 7 raised to the power k plus 2 plus 8 raised to the power 2k plus 1. Therefore, we are transforming this 7 raised to the power k plus 3 plus 8 raised to the power 2k plus 3 into the form this one. Next, since we can't take 7 as a common factor from these two terms, therefore we write this 8 square, that is 64, as 57 plus 7. If you write the 64 as 57 plus 7, then 57 plus 7 into 8 raised to the power 2k plus 1, we can take 7 as common. If we take 7 as a common factor, 7 raised to the power k plus 2 plus 8 raised to the power 3k plus 2 is left, and 57 8 raised to the power 2k plus 1. As this is being a multiple of 7, so obviously this is divisible by 7. This is being a multiple of 57 as divisible by 57. And according to assumption step, 7 raised to the power k plus 2 plus 8 raised to the power 2k plus 1 is divisible by 57, and from this we can say that 7 multiplied by this is also divisible by 57. So the sum of these two is also divisible by 57. And I am going to leave an exercise for you people. Exercises use mathematical induction to prove the De Morgan laws for n set. Here you have to show that union of I is equal to 1 up to union of I is equal to 1 up to n, say AI whole complement is equal to union of I is equal, intersection of I is equal to 1 up to n AI complement. You should use mathematical induction technique in order to prove this De Morgan law. Similarly, you can also try the second form of De Morgan law, that is intersection of I is equal to 1 up to n ai ka whole complement is equal to union of I is equal to 1 up to n ai complement with the help of mathematical induction.